Alright, let's move on to the next problem, number 79. Now we have a weak acid. So we have a weak acid here and a strong base here. We have no choice but to accept this as a weak acid strong base titration. Okay, so the reaction here is this. If we go ahead and do the double displacement reaction for that, this H and this Na are going to switch places, but I'm going to put the Na in front. So this will be Na C6H5COO aqueous. Now your book gives you a different formula. It's still the same thing. They just put all the carbons and hydrogens and oxygens all lumped together. It's done by a stupid inorganic chemist. Organic chemists would never be caught dead doing that. Plus, H and OH are now together, which is water. We basically discount that. But what's important here is this. If this is the weak acid, then this is the weak conjugate base. And so this is telling us, particularly since this is going to be at the equivalence point, that we are going to be dealing with a situation in which we would have had Henderson-Hausbach in stage 2, but the equivalence points is telling us that this is a stage 3 titration, when the moles of base and moles of acid are the same. How do we know that? They just tell us the equivalence point, and that's where it happens. We're going to prove it up here, or show it up here, not prove it, because we have to take that as a very important aspect of figuring out what is missing in order to get the pH. Okay, so we start with first of all, we need the moles of acid. This is the acid, so 1.24 grams of C6H5COOH. Well, this is 6 times 12, which is 72.0. 5 plus 5 times 1.01 is 5.05. Plus this carbon 12.0. Plus these two oxygens 32.0. Plus one more 1.01. So we put all that together. 72.0 plus 5.05 plus 12.0 plus 32.0 plus 1.01, and we get 122 grams for the mass of benzoic acid. So now, first of all, we know that it's 50 milliliters of solution, so the volume of the acid is going to be 0.05 liters. The moles then, we're going to take 1.24 grams and divide by 122 grams, and we get 0.010. No, that might be 2. I'm going to have to divide that out. 1.24 divided by 122. 0.0102. Yes, I was right. Okay. This is grams per mole, so this is going to give us moles. So 0.0102 moles. Now, we don't know the volume and we don't know the number of moles of the base, but wait a minute, we do know the moles of the base because this is at the equivalence point where the moles of acid equals the moles of base. So if this is 0.0102, then this is 0.0102 moles. I guess I didn't have to put the moles in, I'll take that out. Because that's just going to cramp me for room here for what I got to do next. In order to do the rest, I got to know the total volume, so I need to find the volume of the base. Okay? So, how do I do that? Well, it turns out that if I know that my concentration is 0.1800, or just 0.180 moles per liter of base, and I know that I have, for 1 liter, I know that I have 0.0102 moles, then I can find out my volume of the base in liters by cross multiplying and dividing. So this is going to be 0.0102 times 1 divided by 0.180, and that's going to give me 0.0567 liters. So I'm going to put that right up there where it says volume of base, 0.056 liters, 0.0567 liters. All right, now total volume I can find, I add these two together. I get 0.0167, which is round off to 3 sig figs is 0.107 liters. The moles of excess. There are no moles of excess. So we can forget about that noise. Really? No, not true. Because, why? Because we know we have 0.0102 of this. We have 0.0102 of this. And they do cancel each other out, but they create 0.0102 moles of the weak base. So I get rid of that line that I thought I could put in there, because this is not going to give me a pH of 7, because this is a weak, strong titration, not a strong, strong titration. So this is going to give me 0.0102, but I don't put OH here because it's the weak base, so I'll just put capital B like I did there for the weak base strong acid titrations, or weak acid strong base titration. So concentration then is 0.0102 divided by 0.107, and I get 0.0953 moles per liter of the base. Now, in the weak base titrations, when this occurred, we were going to do a quad form, and because it's the base, we have to use the Kb value of this acid here. So we got to take the Ka, which is 6.3, times 10 to the negative fifth. Is that correct? Negative fifth, yes it is. And then we need to find the Kb by taking 1 times 10 to the negative 14, dividing by that 6.3 times 10 to the negative 5. And I get 1.59 times 10 to the negative 10. That is my Kb. Equals, now, because I have a weak base dissolving in water, this is going to be the reverse reaction now. These two added together to give me this. Okay? So, this is going to be, well, let me write down that equation before I get too ahead of myself. Sodium benzoate again, I'm going to add water to that, but this is going to be weak because there's nothing strong pushing it, and they're going to get the original components back, which is going to be C6H5COOH plus NaOH. Okay, so that means then that I'm going to start with 0.0953 of concentration of the base. I'm going to lose X here, I'm going to gain X here, and I'm going to gain X here. So the Kb, which we said is 1.59 times 10 to the negative 10 is equal to X squared over 0.0953 minus X. Now I'm going to show you a little something here that's going to make your life a tad easier. When we go ahead and multiply this out and add everything and move everything over, negative X squared we know we're gonna get minus 1.59 times 10 to the negative 10x plus, and we know that we're gonna multiply these two together. I'm gonna leave it that way. I'm not even gonna multiply it out. I'm just gonna leave those two numbers there multiplying as my C term. And when you type it into your quad form, you're going to type it in exactly like that. You don't have to type, you don't have to find the answer for that. You don't have to worry about rounding off or any of that stuff. So let's go to quad form. And A is negative 1. B is negative 1.59. E negative 10. And C is 1.59. E negative 10 times 0.0953. And we get the positive value that's going to work here is X is 3.89 times 10 to the negative 6 moles per liter of your OH. That is the concentration of OH. So we're going to put that up there in the chart underneath this right here. So 3.89 times 10 to the negative 10, 10 to the negative 6 moles per liter of hydroxide. And so we're going to take 14 plus the log of that answer, and we get 8.59 as our pH, which is what we would expect when you titrate a weak acid with a strong base. You should get a pH of greater than 7. Okay, go to part 2 to continue this.